I hope everyone's doing well. I'm Mr. Ish. Thank you for joining me for this video. Trigonometric approximations using derivatives. Very fun. We've seen something like this very recently, but doing root approximations. Here we're doing trigonometric, focusing on sine and cosine. The basic gist of something like this is if you have a function f of x, you know that is equal to y is equal to a specific item, whatever that might be, a specific function. We will just represent it like that. Then when you're doing the derivative of this function, you can represent it as dy over dx is equal to a specific function. We'll put an x here as our input. You're doing the derivative of that function, you're looking at something like this. There are four things which stand out over here. You have an x, you have a y, you have a dy and a dx. You have x, you have y, dy and a dx. These are the items you need to find for these type of approximations. It seems intimidating, but it's actually very easy. At the very outstart, you need to know two derivatives, but in a future video I'll be explaining to you why these derivatives exist. The first item you need to know is whenever you're looking at the sine function, the derivative of the sine is always equal to a cosine. Derivative of sine x is equal to cosine x. This is something you just memorize. The other item you need to know is the derivative of the cosine is equal to a minus sine x. Why the derivative of sine is equal to cosine and why the derivative of cosine is equal to minus sine x is not being discussed in this video, because I'm going to talk about that in a very upcoming video. You just know this for this video. Sine derivative is cosine, cosine derivative is minus sine. You have to know x, y, dy and dx for these type of approximations. The determination of those four items is very easy. These derivatives are very easy to remember. So let's look over here at sine 32 and cosine 86. How can we use derivatives to make these calculations without relying on a sine and cosine function on your calculator? Start here with sine 32. This is our question. We have to do sine 32. You know it should be somewhere close to a known value, which is sine 30. I have a function here which is sine 30. If I look at this function sine 30, it's equal to 1 over 2, which is 0.5. I'm looking over here at a specific function which is inputting an x value and I'm getting a y value. Sine of this x value 30 is always equal to a y value which is 0.5, and I've already determined x and y. X here is equal to 30 degrees, y is equal to 0.5 or 1 over 2. Let's look over here at dx. I'm looking here at 32 degrees. I have a known value 30. This right here represents an x value. This here represents another x value. Your dx is always equal to your delta x. What is your delta x? You're seeing what is needed to get you from your known value to your test value or the value you're interested in. My known value is 30. I'm looking for 32. What is the delta x? It's a plus 2. Plus 2 degrees, because 30 plus 2 gives you 32. You know dx here is equal to plus 2 degrees. Now, when you're doing trigonometric approximations for this particular item here, dx, the answer here, which is plus 2, must be expressed from degrees into radians. So you really have to multiply this plus 2 by times pi over 180. I have over here my dx 2 pi over 180, or you can just say pi over 90. Consider again dx. dx is equal to delta x. The difference, or what you need to get from one value to the next, that's your delta x. But you're going from your known value to your unknown value or your test value or your experimental value. 30 plus 2 gives you 32. You convert the degrees into radians, and that right there is your dx. And dy is not hard. To bring out the dy, you now do the derivative application. You know y is equal to sine x, but I've told you from the outstart, you're taking this on face value. The derivative of sine x, dy or dx, is equal to the derivative of sine x, which is cosine x. You're solving over here for dy, push the dx over there. Dy is equal to dx cosine x, and I have all of these values right here, dx and cosine x, they're right over here. What is my dy going to be? My dy is going to be dx, which is what? Pi over 90. What is my cosine x? X right here, you know to be 30. You're doing cosine of 30. You know cosine 30 from your trigonometric ratios. They're easy. You have a 30, 60, 90 triangle. Here's my 30. This is a 1. This right here is a 2, root 3. Cosine of a 30 is equal to adjacent over a hypotenuse, which is root 3 over 2. So I know dy is equal to pi over 90 times root 3 over 2. My dx times my cosine x. X here is your known value 30. So I know now my dy is equal to, I'll combine these. I have a root 3 pi over a 180. This pi is not in the radical, it's just root 3 pi 180 as your denominator. So we've determined my dy, we've determined dx, we've determined x's and y's. How do you determine your approximated value? It's a formula. Approximated value using derivatives is always y plus dy, and you have these values x, y, dy, dx. As a quick rehash, you have 4 items you need to determine. X is your known input, y is your known output. I have a known function sine 30, it has a known output 0.5. That's my x and y. My dx is my variance or my delta x from my known to my unknown. But my known to unknown is a plus 2, but you convert that into radians. Times it by pi over 180. Your dy comes from your derivative procedure. My approximated value for sine 32 is equal to y. What's my y? It's a 0.5. What's my dy? It's this, root 3 pi over 180. Do this calculation, you'll have a good answer. Let's bring out our calculator. I'll do this part and I'll add 0.5. Root 3 times pi divided by 180 plus 0.5. I'm getting here 0.530229. Let's write it out. 0.530229. I do not need this value to be close to this value. No, I need this value to be close to the calculator value for this. This right here is just my known standard value I'm using to help with the derivative procedure to approximate something I do not know. I'm getting sine 32 using derivative procedure approximation to be this. Let's bring out our calculator and see what sine 32 really is. Sine 32 is 0.5299. I have 0.53. If I take this 299 and I round it up, I have 0.53 and it's good. This value here is good and I'm happy with it. Again, you have to determine x, y, dx and dy. They run through this approximation procedure and your ultimate formula is this. Approximation value is equal to y plus dy. Keep in mind this dx must be expressed in radians, not in degrees. Let's look here at cosine 86. Second question, we're looking right here, cosine 86. I know cosine 86 should be close to a known cosine value, which is a 90. Here I'm doing cosine of an x value, cosine of an input equals an output. You know cosine 90 is always equal to 0. You can run that on your calculator. It's an x-intercept on your cosine function graph. I have to determine x, y, dx and dy. Dx must be in radians. I have here x's and y's coming from my known values. A cosine of an x value, which is 90, is equal to a y value, which is 0, and that's done. Let's look at our dx. Dx is the same thing as delta x. I'm looking at 86, I'm looking at 90. Here's an x value, here's another x value. You go from your known value to your unknown value or your test value, your experimental value. What's the delta x? I'm doing a 90, it's a minus 4 degrees. 90 minus 4 gives me my 86. It's a minus 4, but you gotta multiply it by pi over 180, convert it into radians. Minus 4 pi over 180, and we'll just hold it right there. That's my dx. I need to now determine my dy. For the dy, you're always using a derivative. Y is equal to a cosine x. The derivative of this function which I gave you at the beginning, you're just accepting this on face value, because in another video I'll show you these two derivatives, why they are what they are. Derivative of cosine x is equal to minus sine x. Solve for dy. Dy, you push this on the other side. I have a minus dx sine x. This right here is going to be my item which will give me my dy. You've seen this. Let's bring our values in play. Dy is equal to minus. What's my dx? It's minus 4 pi over 180, which I can simplify to minus 2 pi over 90 times sine of x. What's my x value here? It's sine of 90. You know sine of 90 is a 1. We'll just remove it. This is all what I have for my dy. The minuses will cancel out. I have a 2 pi over 90, or I can just say pi over 45. That's equal to my dy. Pi over 45, and we've determined it. And it should be good. Now all that remains is to determine our approximated value is always equal to y plus dy. And it's going to give me the value of cosine 86. The value of cosine 86 should be close to 0, but it doesn't have to be. The formula should give you a value which is close to the calculator value for this, and that's what our goal always is. The approximation should match what your calculator is or be very close to it. What's my y value here? It's 0, because cosine of 90 is a 0, plus pi over 45, which is my dy. I bring out my calculator. My calculation for approximated value is really only just pi over 45. Pi divided by 45, I have 0.069813. Based on my derivative procedures for trigonometric approximations, this is what I get. And I'll hold it right over here. I won't add in any more digits. Let's bring our calculator and really see what 86 cosine is. Cosine of 86 on the DEG mode is a 0.069756. We're really good. I have 0.0697, I have 0.069, but here I have 813. But look right here, it's 756. The 756 can be rounded up to an 8. So I have a 0.0698. Here I'll have a 0.0698, and we're good. We're happy with it. And it's done. Keep in mind these trigonometric approximations are good, and you're using your derivatives. You're doing an x and y. That's coming from your known items. Your dx, delta x, is always expressed in radians. The variance or the delta difference between your known and your test value. That's what it is, your known and your exam value, your test value, or your value you're interested in. Your dy comes through your derivative. And that right there is the end of this video. But keep in mind, we focus here only on sine and cosine. These trigonometric approximations can be used if you know the derivatives for any of the 6 trigonometric functions, not limited only to these two. Here in this video, I'm only limiting to these two because we haven't learned the derivatives of all the functions. We know sine and cosine, and the upcoming video will show you why those derivatives are the way they are. Thank you for watching.